Hi, this is Christopher Maloney talking about how a star is born, how, when, and where. So take a minute to think about how you think that actually took place. Life cycle of a star starts off here as a nebula, very thin gas cloud, getting to be a darker dust cloud, finally a globule, then a protostar. It can go down and be small and be a brown dwarf, which is going to last a very long time. Or it can become part of a main sequence stars, go into a red giant. Red giants are actually burning off their outer core very quickly, and then down to a white dwarf or of a black dwarf. Black dwarf is going to be very, very small. If it condenses down and much larger, it can actually become a supernova, it can blow up, or stay as a neutron star, which is very dense again. If it's large enough, it can actually become a black hole. That ends kind of the life cycle of the star. This is the universe. It is both infinite and expanding. Each one of those dots is a cluster of galaxies, not a galaxy, not a billion stars, but a cluster of galaxies. And the yellow spots are actually superclusters of galaxies. So it's just worthwhile thinking about the universe is basically not uniform. It has areas of very dense superclusters, and it also has areas of very almost empty space. It's very interesting from an idea of an explosion. How did this explosion take place? And here's a little star baby. This is our star baby right here. It's just starting off a little proto-star. You can see its little proto-eyes and a little proto-mouth. Yay, star baby. And just like regular babies, star babies can have tantrums. They can actually give off huge jets of clouds that come off of them. These are actual images from the Hubble telescope that show these dense areas of cloud coming off of a protostar. And here you see star temperature. So color determines temperature. You've red to blue. And what you want to think about is how long will the stars last? Will a cooler star last longer than a hotter star? Will a hotter star actually last longer than a cooler star? Our longest stars are red dwarf stars. They last for trillions of years. Our sun is actually a yellow dwarf star, has a lifetime of about 10 billion years. If our sun was much larger, not only would we burn to a crisp, it would have lasted only a few million years, so we would be long gone by now if we had a larger star as a base. And here's our sun, Sol, our dwarf star, a yellow dwarf star, sequence G dwarf star. It's actually a white dwarf, but it appears yellow through our atmosphere. Now, our star actually just uses a power of the condensing atmospheric power of the gravity to push together protons to make hydrogen into helium. But that's as much as it can do. It can only do that action. If it was much larger, it could actually do the carbon, nitrogen, oxygen cycle, or it could actually generate much larger stars. And in order to generate the much heavier elements, we have to have two huge stars crash into each other, and they will actually generate your uranium, your plutonium, your heaviest elements. So I've drawn the equation E equals mc squared, which is the equation of how long a star will last. In this case, if the star were to actually blow up all at once, it would be gone. So it's E equals the fraction of the mass of the star that's burning at any given time. But you can actually tell how long a star is going to last or how long it has lasted, given how much of a fraction of the star is being burned at any given moment. There's a bunch of different types of stars, from protostars to supergiant stars. If a neutron star, if it was about twice the size, our sun would actually crush itself down to a neutron star. It actually can even become a black hole if it got larger. There's also things like quasars, which aren't really stars at all. They actually give massive quantities of radio waves out. We can get those radio waves, but they tend to be fairly constant. They're not coming in little bursts, which is what we've experienced from other things that we think might be aliens. There are also pulsars, which actually give you pulsating radio waves, which are very scary if you don't know what you're looking at. And they're neutron stars, but they spin and then they pulse out electromagnetic radiation that can actually give us very high energy cosmic rays, which are not great for human life. And you can use a pulsar's beeping to actually use as a timepiece. So if you're out in space, you could actually use pulsars for beeping. And then there are magnetars, which are actually huge magnetic fields that are stars. If that was in Star Wars, you'd actually have the ship entered out of hyperspace and then crash right into the sun because it was actually pulled in by a huge magnet. And if you go to YouTube, you can watch the neutron star forming with Kurzarzt. And they have a whole range of topics on this area. That's it. Thank you very much.